is in purple, voltage for the resistor. And then the current across the resistor, or the current coming out of the power supply, it's the same thing. They're all in sync with each other, they all peak at the same time, they trough at the same time, they hit zero at the same time. They are called in phase. Brooke.
Does current have like a smaller slope because it's like divided by R?
Yeah, except I didn't tell you what R is. It's a different, it has a different peak here, it would have a different slope. It's also on a different scale. The units here would be amperes and the unit here would be volts. So it's, how do you present? I wanted to show that they were in phase, but they're on two different scales.
Okay. So R isn't resistance?
R is resistance.
It is, okay.
Yeah.
It just means something different in this context.
That's still resistance. I mean, this value right here, this would be whatever that value right there is. That's your maximum
Okay.
voltage divided by R. Whereas this right here is whatever that maximum value is.
Okay, thank you.
Is there just one line for power supply?
There's two there. The purple is over top of the black.
Oh.
They're together.
Okay.
Conceptually, I don't understand why they wouldn't be opposite. Like, why would it be a negative sign graph? Because it seems like what you gain over the power supply, you lose, over the resistor.
Yeah, okay. I had to ask that.
Or don't, you can just skip it. You know what? I figured it out, let's move on.
Because if I was actually gonna measure the voltage, so I put one probe here and I put the other probe here, I would get the same value across here as I got across here. So if this is like the low and the high, I get the same value. That's why we take into account the fact that we lose it by throwing in the minus sign at that point. That's not a look of, oh, of course.
Oh, of course, Dr. Foss. Sorry, I am content with your answer. I will think it over.
Okay.
Thank you.
I will think it over.
Chew on it.
Yeah, we're gonna be doing that several more times, and also when you do the lab,
Right.
not Wednesday, but the week from Wednesday.
So even if you switch the probes, it wouldn't have like the same value, but the opposite sign?
Yeah, if I switch the values there, then this would, they'd both be negative together, both positive together. The potential difference between between 2 points is the same regardless of the path you take.
Different.
So taking that path or that path gets you to the same spot.
Okay. Right, because going backwards over the resistor would be like going forward over the power supply. In terms, like when we did our
Yes,
formulas.
yes.
Okay, I can accept that.
Okay. Any other questions? Sorry, did not mean to discourage you from asking the question. It was just, most students just sort of feel okay and just move on.
Well, that's me. I'm accepting that. I'm just gonna take it, yeah.
You know, I'm a deep
Let it
diver.
flow over you.
Yeah, let it wash over me like the holy water.
What exactly is in phase, and what does that mean?
In phase means that if I actually did a plot of, if I had some AC circuit where all I have is a AC power supply and a resistor in it, that if I actually looked at the voltage at first time, that the voltage first time for the two of them would increase at the same time, they decrease at the same time. They have the same phase shift, that they're not, if they're out of phase, would look like this. If one of them were like this, the other one were like that, that's out of phase.
Oh, I see. Okay. So the periods kind of like have to be the same, right?
The period would definitely be the same.
the sine graph and the negative sine graph be out of phase as well, because one is peaking, one is troughing, or because
Yeah,
they're at
that-
the same time, they're still in phase?
No, the fact that they peak and trough at different times, they would be out of phase by
Like,
pi.
That's like the maximum they can be out of phase.
Hmm, okay.
All right. I'm about to expose you to a different way of looking at the exact same thing. Okay, here we go. So imagine I have, picture this as an overhead view, and I've got a spinner on it. So think about, the game of life has a wheel that you turn.
The game of life?
Yeah, does it?
Isn't he
Yeah,
like
it does.
Twister, where you like
Yeah,
flick
Twister
things?
has-
There we go, Twister,
Yeah.
yeah. So Twister, you got a little arrow there, you can flick it, the thing goes spinning around. So as it goes spinning around, then actually, I wanted to start with sine, that's really messing me up here. Going to zero, going positive, so that's spinning around going this way. Ugh, I wanted to spin the other way.
Challenge yourself.
So I flick it, we want it to spin, it's gonna spin counterclockwise, the classic math definition of the positive direction. So it's gonna spin at some angular speed of omega. The exact same thing as the omega at the rate that this thing is spinning around. If I look at the projection onto the horizontal axis. So projection on the horizontal axis is 0. When the arrow is over here, I'm at my maximum projection. Basically, think of a projection as if I had a light source down here, it's the shadow it would make on this axis. So as it spins around, the shadow would basically start at 0, then reaches some peak value, then it drops back to 0, then goes to some negative value, then goes back to 0 again. Everyone good with the shadow analogy, because it's gonna get more complicated from here.
I'm actually not comfortable with that.
Okay.
So, sorry,
No,
but
I'm
that
not
doesn't make
gonna
sense,
either.
it seems like you would cast just as much of a shadow when it's on the opposite side, why would that be the most negative? But it would be the
No,
most.
it's most negative when the arrow's over
But
here.
how is that? Because the shadow would be just as large if the light source is coming from down here.
Yeah, where is the light source coming from?
All right.
Oh, that's the light.
I'm gonna change that to, see, I'm trying different
Do we do-
explanations
yeah,
here, just to see if I can,
Maybe we should do the cosine. Maybe we should just do cosine if that's what we're gonna be doing.
yeah, let's,
Okay, Harrison's right, yeah? Whatever is most practical for us.
I wanna learn that way, but not if it's gonna just confuse me more.
Right.
I don't wanna learn it.
Harrison.
I wanna do cosine.
all right. That's the basic cosine shape right there. Let's put a cosine in there, cosine in there, cosine in there. So imagine that the arrow is pointing over here. I can put my light source above it, and I'm looking at the shadow on the ground. It's still horizontal, it parallels this. So this arrow here, I've got some right there. This is gonna go spinning around, making noise. So it starts out with my shadow being that long. When the arrow is here, my shadow is the smallest. When the arrow is here, excuse me, my shadow is pointing in that direction. Basically, there's my shadow. Then when the arrow is down, pointing downwards, my shadow is 0 again. So I get maximum positive shadow to 0, maximum negative shadow, 0, maximum positive shadow. Maximum positive, 0, maximum negative, 0, maximum positive.
That makes sense.
Okay, this is known as a project, you're projecting onto the horizontal axis. This arrow is moving around at angular speed of omega. This arrow has a name. It is called a phasor.
Cool name.
An OR.
With an OR, yes.
Wait, so what is the phaser? It's like the line.
It's this arrow that goes spinning around.
Okay.
It's the twister arrow in the middle. That gets flicked, but it's on a frictionless surface, so it spins at the same angular speed the entire time. VR and IR are in phase, which means that if I had, since I basically have two quantities here, I have this voltage of the resistor and I have this current up from the resistor, or going across the resistor, I have two arrows, one arrow for each of those. Now, I don't know which one's bigger than the other one, but I've got two of them, and I have to draw one of them bigger than the other one. So I'm just gonna make this black one I sub R, and I'm gonna make the purplish one V sub R. Because they're in phase, those two arrows will always be together. If you're thinking, that doesn't seem so hard, wait till we introduce capacitors and inductors. But this is one of the rules when you're dealing with a phasor diagram with for AC power, well, you wouldn't really do it with DC, but for the phasor diagram, I sub R and V sub R are in phase. They hang together. They're always pointing in the same direction. The magnitude of these arrows is just the maximum value. Because the V sub R is at a maximum value, got the maximum shadow here, this length right here would be whatever the maximum voltage across the resistor is. And so the maximum, so length of these, of VR phasor, no real set notation on that one obviously, is just maximum voltage across the resistor and using a capital V, lowercase r there.
Did you say lowercase r? Did you mean like a
Or
subscript?
capital V with a subscript r. And then the magnitude of my I sub R phasor would just be capital I sub R. In this case right here, so specifically, so these rules right here are gonna be true. As we make it more complicated, these rules are still true. For this one simple circuit right here, V sub R would be epsilon, whatever the EMF is there, the maximum voltage produced, divided, actually just the same thing as epsilon. And capital I sub R is epsilon divided by R. What we have circled in red here, there and there. It's just the amplitude of those two functions. Controversial enough where a student just goes storming out.
Yep. It's classic work here.
If you hear the door slam, you know why.
Yep.
All right, here we go. I'm gonna about to erase most of this.
I'm curious if this is just your mood, or if like the material is daunting enough that like you're prepping us on purpose.
Very eerie on the
Yeah.
right.
Yeah, the AC stuff, it's kind of, to some extent, it's kind of like the momentum lab. I don't know, did I do the momentum lab with, I guess we've got representatives from various groups here.
I can't
Will you
remember.
enroll?
Yeah.
Did we skip that one?
That's the one where you get the two cards, you need to make sure that the motion sensors at the ends are lined up just perfectly, or at least within 1% of each other. And then you smash the two cards and take into account how much they slow down between when you let loose to when they hit.
I didn't.
I don't think
remember
we, yeah, I
that.
don't think we did that.
Yeah, okay, that's the lab that usually near the end of the semester, and the lab that, even if people have been keeping up all along, they get to that lab and just, there's something about it that's just overwhelming. The AC lab has some similar effects, and so I'm hoping to avoid that. It's a great lab because for one of the places where you're finding percent error or percent difference, if you are above 1%, you've done something wrong. That's how good some of those results are. All right, so we got those rules up there. Let's make a capacitor now. So delta V from the power supply plus delta V from, although I'm dropping the delta at some point, of the capacitor is equal to 0. Same start as before. Epsilon cosine of omega t minus VC is equal to 0. We get epsilon cosine of omega t is equal to VC. All that, nothing earth shattering there. Brooke?
This feels like a very basic question, but where do we does the same, law apply here where it's like we gain voltage, where it has to be equal to 0?
Yeah, whatever we gain here, we're gonna lose 0. If we go around and end up back where we started.
Right, but it's a capacitor, so doesn't that?
Still holds true.
Okay.
Because because they're gonna have a positive and negative side. So which side is positive, which side is negative is gonna flip back and forth. But if we take a moment where this is the positive side, that's the negative side, this would be the positive side of the power supply, that's the negative side of the power supply at that moment.
So it flows from positive to negative.
Current will flow from positive to negative.
Right.
The electrons flow the other way. And then when this flips, then current flows the other way.
Okay, that makes more sense, because I guess in my head I was like, capacitor is the opposite of resistor in terms of voltage, so where do you lose voltage for it to be equal to 0 again, but that makes sense.
Okay, but you're good now.
Mhm.
All right.
Can I ask one question about
Yep.
epsilon? This has nothing to do with permittivity of free space, that's
Correct.
like EMF.
Yes.
Measured in volts.
Yes.
Okay.
EMF is just sort of an ideal voltage. Now the voltage from a capacitor, let's think about capacitance is charge divided by voltage. So voltage is charge divided by capacitance. So this would be, modifying it for AC, this would be the charge on the plates divided by capacitance. This is what we did when we were dealing with DC up until now, and now we're dealing, the charge on the plates is gonna constantly be fluctuating.
So the little Q is the charge on the plates,
Yes, the instantaneous charge.
like on one plate or the other?
Yeah, with capacitance, you have the same magnitude of charge on both, just one's the negative of the other one.
So this is just the absolute value, whatever that number is. Like one of the plates is positive, one is negative, and it's just the value.
This was the absolute value, this was just actually the charge on the positive plate. This would be the charge on, presumably, depends on how you, trying to avoid getting into the minutia quite yet.
Okay. Then it's okay.
That's the charge on a plate, so it would start out with a positive charge on that plate, and then it would go to a negative charge, so Q is actually gonna oscillate back and forth, this is not an absolute value.
Anna, stop asking these good questions today.
If I don't understand it, then I just don't know.
No, I understand, and I'm not trying to dismiss it, it's a question, at what point do I introduce which bit?
It's totally valid to say we're gonna cover that later, I'll be fine. Thank you.
What's the relationship between charge and current? Because ultimately, when I'm doing phasors, I'm gonna have a phasor for voltage, I'm gonna have a phasor for current. I wanna know what about the phasor for, and I have, I could produce one for charge, but that's generally not done. What I wanna know is the relationship between Q and I. What is current? Going back to DC stuff.
Is it VR? VR?
Thinking Ohm's law.
Ohm's law would be V over R, or delta V over R. I'm looking for the relationship with charge.
I'm nothing without my formula sheet. Let me see.
Yeah, me too.
And we established earlier that